If you look up near a major highway or outside a power plant, you'll see them. Massive transmission lines, thick as your arm, carrying the electricity that powers our modern world. Given the sheer scale of this infrastructure, you might assume these giant cables are solid, heavy metal all the way through. But strangely enough, many of the thickest wires hanging up there are completely hollow on the inside. To understand why, we first have to look at how electricity normally flows. In a simple battery-powered system using direct current, or DC, the electricity acts like water flowing through a pipe. It utilizes the entire cross-section of the wire, from the very center all the way to the edges. This perfectly uniform flow is incredibly efficient. Because the current spreads out evenly, it takes advantage of every single millimeter of space available inside the metal. But our national power grid relies on alternating current, or AC. And when you pump alternating current through a thick wire, it behaves completely differently. Hollowing out these cables is a precise engineering response to the physics of alternating current, a design that reclaims efficiency from a force that would otherwise waste tons of metal. Unlike a battery that pushes energy in one steady direction, alternating current constantly reverses its flow back and forth. This constant sloshing motion generates a shifting, invisible magnetic field deep inside the wire itself. Notice how the bright blue electricity isn't spreading evenly in this AC wire diagram. Magnetic fields push the current outward to the skin. Below, orange arrows show eddy currents swirling in the opposite direction, canceling internal flow and leaving the core as dead space. Because all of the electricity is suddenly forced to travel along that narrow outer rim, you end up with an electrical traffic jam. Just like forcing a 4-lane highway into a single lane, cramming electrons together creates friction, and the laws of physics dictate that this will cause a sharp increase in the wire's overall resistance. Higher resistance is the enemy of an efficient power grid. As the electrons struggle to push through that crowded outer layer, valuable electrical energy is lost, bleeding out into the surrounding air as waste heat. This phenomenon is known as the skin effect. It places a physical limit on solid AC power lines by drastically shrinking the amount of metal that can actually carry power. But the challenges of AC power don't stop at the surface of a single wire. We also have to consider what happens when engineers run two separate AC transmission lines closely parallel to one another. This illustration demonstrates the proximity effect. On the right, magnetic force fields of adjacent wires expand and interact. When currents flow opposite, Verkelling fields shove electricity to the extreme outer edges. Conversely, parallel currents create attracting fields, pulling electricity to the inner edges facing one another. In both of these scenarios, the crowding creates an even worse traffic jam than the skin effect alone. The available current is crammed into an incredibly narrow, asymmetrical sliver of metal, which chokes off the flow of energy. With the proximity effect, these lines face a two-front battle, struggling against internal pressure and the magnetic interference of their neighbors. This compound interaction spikes the temperature and leads to even higher energy losses. This brings us back to our initial mystery. Engineers purposefully build giant power cables hollow, because the skin effect renders the solid center completely useless for AC transmission anyway. Looking closely at the design solutions section of this diagram, the economic logic of the hollow conductors becomes clear. By removing the center, power companies eliminate tons of heavy, expensive metal from the dead core without sacrificing a single drop of electrical capacity. But that still leaves the problem of the proximity effect. How do engineers prevent parallel lines from magnetically interfering with each other when they share a tower? The answer is physical separation. Rather than running one massive cable, they use bundled conductors. They take multiple smaller cables and physically lock them apart with rigid hardware spacers. By artificially widening the gap, they weaken that magnetic interaction. For complex, smaller-scale electronics, the solution gets even more intricate. Here in the diagram, you can see an illustration of Litz wire, a specialized cable made of hundreds of tiny, individually insulated strands wrapped together. The clever trick of Litz wire is how those individual strands are woven in and out of the center. Because the wires constantly crisscross, every single strand gets a turn at being on the outer skin. This forces the electricity to distribute itself and utilize the whole cable evenly. Electricity is constantly being pushed and pulled by invisible magnetic forces that continually try to restrict its flow. But by cleverly shaping our physical infrastructure, whether that means hollowing out massive aluminum cables in the sky or carefully weaving tiny copper strands in a lab, engineers have found a way to outsmart the physics and keep the grid running.